This is the outline of this lecture. So first we'll see what is a rectifier and what is a half-wave rectifier. Then we'll see what is a full-wave rectifier, and basically we will discuss in details the working principles of the center tape as well as bridge full-wave rectifier. We'll discuss the merits and demerits of each of these two rectifiers. And then finally we will see what happens if we connect a capacitor with the rectifier, the capacitor as a filters, and then at last we will simulate all the different types of rectifier, half wave, full wave, rectifiers, and also with capacitors in LTSpice. So basically, what is a rectifier? The rectifiers are those circuits which will convert the AC to DC. For example, we have our laptop, we have our mobiles to charge, right? And the source of the power that we have is our AC mains, right? So our AC mains, which is basically you have 220 volt. 220 volt means this is RMS, okay? This is VRMS. So if you multiply with root 2, it is the amplitude of this voltage is around 311, okay, and of course 50 hertz, okay. So this is the power source that we have, and on the end we may have our phone, right? We may have our phone, and the because the USB is 5 volt DC, right? It requires a 5 volt DC, okay. So the rectifier circuits are basically those circuits which will convert these AC, whatever the AC mains that I have, and finally what I want to get is a constant 5 volt DC. So this is my rectifier circuit, okay. So this is my rectifier, okay. So this is the aim of this discussion or this lecture, right? Finally I want to get a constant 5 volt DC. So we will be using the PN junction diode to get the rectified DC, but of course we will not get it directly. We have to go step by step, okay. So we'll proceed step by step and see how a rectifier circuit can be achieved. So first step is we will go for a half wave rectifier. We will see what is a half wave rectifier. We will see why it is called half wave, and then we'll see the full wave rectifiers, okay. So we have the full wave rectifier. In full wave rectifier we will see two types of rectifier. One is the bridge, the other one is this center tape, okay. So let's start with the half wave rectifier. Okay, so I have my AC mains here as discussed. It's a 220 volt VRMS. And of course it has to be down converted, and of course we have the ratio. We can use maybe N2:N1, right? We notice a transformer, and based on the knowledge that we have for the transformer, we can easily down convert. Down conversion is necessary because we only want maybe 5 volt or 10 volt, or for most of the circuits it will never go beyond 15 to 20 volt, right? It will be lesser than that. So we need to do the down conversion, right? The DC voltage is very small. So and then what we can do is we can put a PN junction diode here, and of course here we'll have a resistor. Let's assume we have grounded it here. So I want to know this V out. Let's call it as diode D1, and let's call this as V in, okay. And this dot represents that the direction of the flux, okay. So and of course positive and negative, okay. Yeah, So now what will happen is, because this is grounded, only when this is in the positive half, the diode will be doing the conduction. So let's try to analyze the circuit. So if you see here, when my V in is less than VD, right? When this voltage V in or this voltage is less than VD, as we know that VD may be around 0.7 volt from our constant drop model. So when V in is less than VD, this diode D1 is off, so my V out will be 0. Okay, 0, D1 is off. Whereas when my V in becomes greater than VD, right, my V out will be equal to, so this is in forward bias region and there will be a drop of VD, so V out will be equal to V in minus VD. Okay, so I can draw a graph of this equation, and this type of graph where we are trying to relate the input with the output, right? In one axis I'll be drawing the output and in the other axis I'll be drawing the input. This is called the input output characteristics. So my x-axis will be the variable, which is basically my V in, and y-axis will be my V out. Y-axis will be my required V out, right? So, and V in is the input variable. Okay, so now let's try to draw this equation. When my V in is less than VD, V out is always 0. So it's 0, like for whatever the value of V in may be. Okay, and as soon as V in is greater than VD, V out will be equal to V in minus VD. It is something like this. Okay, it's a straight line. If you see, this is with a slope 1, right? And we can see that the x-intercept is VD. Okay, so if I make V out 0, the V in is equal to VD. So this slope is 1. This kind of graph is called the input-output characteristics. So this is the input-output characteristics of the half-wave rectifier. Okay, so now if I try to draw the time domain response, right, of this half-wave rectifier, so let's try to draw it. So this is my V in, okay, and yeah, so this is my sine wave that I have applied here basically, and I want to find out the V out. Okay, so if you see here, when this V in is less than VD, it is still off. Okay, it is still off and V out is 0. Okay, but as soon as it will reach the VD, the diode starts conducting and V out will be equal to V in minus VD. So as soon as it is reached, the V in reaches this VD, 0.7 volt, then it's going to follow something like this. Okay, it's going to follow the V out, and finally it's going to reach something like this. And this is, let's call the peak voltage to be BP. Okay, so now, and of course, when this is lesser than VD, this will be in off condition. So it will start continuing something like this till this point again. Okay, and then it's going to repeat. Okay, so the important thing here is only half of the wave has got rectified. The other half is not rectified. Okay, so partially we have done the rectification. Of course, it is not DC at all. okay, or some DC, or at least it is not going in the negative direction, okay, but still it is still pulsating, okay. So we need to make it constant, but this is a first step, I should say, okay. This is the first step of the rectification, okay. So here I need to use the other half as well, okay, because my other half energy is getting wasted. So if I can make some arrangement, right, if I can have some two pairs of something like this configuration, where one diode will be doing the rectification of this positive half cycle, and the other diode will be doing the negative part. So this will lead to the full wave rectifier. But before discussing a full wave rectifier, let's try to analyze one point, okay. So when this diode is in the reverse bias condition, what is the maximum reverse bias voltage it is experiencing, okay. Let's try to analyze that, because this point is very important. So this is the state, or this is at this point the diode is experiencing the maximum reverse bias voltage. So in this condition, the output is 0, and this is at minus BP, okay, minus BP. So if you see here, the maximum reverse bias voltage, right, the difference between A and B, right, this is at higher potential. So, or the mod of, basically the mod of, or whatever, you can do this minus this as well, no problem. But the voltage difference is 0 minus BP, so which is VP, right. So in this case, the maximum reverse bias voltage that it is experiencing is equal to VP, or the amplitude of this Vin, okay. So this term is called peak inverse voltage. PIV in this case is BP, okay. So this is basically the peak inverse voltage. PIV is occurring here, okay. Yeah. So let's go to the next type of rectifier, where we are trying to use both the sides, and we'll get the full wave rectifier. Okay, so this is my full wave rectifier. So basically it has two half wave rectifiers, and they are combined, D1 and D2, right? And of course here this is important, that the direction of this input voltage V in and V in that is getting generated, it should be same, okay? But of course, because we have grounded here, okay, ground as a reference point, of course, it is not necessary that you should ground it. You can give other voltage as well, but the point here is, because considering this as a reference point, ground, okay, so here it will become, suppose during the positive half cycle, this will become BP, right, and this will become minus BP, okay. Okay, so this was the this upper half which is doing, okay, and now because you can see here that because this is the ground, this one is the ground, and this is V in, so this will be exactly opposite, okay. So it's basically something like this. So if I have some source here, okay, so which is maybe 5 volt, okay, 5 volt. Now if I connect the ground here, okay, connect ground here, so definitely this node will be 5 volt. Now if I take the same voltage source here, like this, with the same polarity here, and if the node, that voltage that will be experiencing will be minus 5 volt, okay, so negative of whatever I am getting here will become here, okay. So that means it will be just inverted by 180 degree. So minus 1, we know that it is a inversion by 180 degree, okay. So this is the inverted voltage, okay. So this is my, let's call, okay, so this is the voltage at the VA, black color word is the voltage at VA, and let's call it as VB. Okay, this is VA, and the blue color one is the VB. So this is what I'm going to get. So the VA is basically the voltage here, and VB is the voltage here, which is inverted by 180 degree, and this is what I will get across V out. The red one is the V out. Finally, the V out at across this load resistance RL. Okay, yeah. So now in this case, let's try to analyze the peak inverse voltage of these, peak inverse voltage of this full wave rectifier. By the way, this rectifier is called center tap, because in this transformer there is a tap at the center, right? A tap at the center is required for this kind of transformer, and the flux that is going, so it should be equally distributed to both these N1 and N1. Okay, so then only this will work, because we want here, which is perfectly 180 degree phase shift of this VA. So this is a requirement of this kind of center tap rectifier. So this is a full wave center tap rectifier. Okay. Yeah, so now let's try to analyze what is the peak inverse voltage. Okay, so in this case, what is happening is the D1 is conducting here, D1 is conducting, and D2 is not conducting. In this case, D1 is on, but D2 is off. Okay, so then I need to find out what is the peak inverse voltage across D2. So D1 is on, means if you see the V out is here BP minus VD. So here the V out will be BP minus VD. Okay, this will be at this node. So you can see here, right? V out. This is basically my V out. So the red color is V out, right? So this is V in minus VD. Okay, and now now here it is basically at this point, like VB, the voltage VB, you can see here, the voltage VB at this point here, it is, that it is minus BP. So at this point is minus BP. Okay, so if I see the peak inverse voltage, so it will be this minus this, right? So which is VP minus VD minus of minus BP, so which is 2 BP minus VD. Okay, so therefore the peak inverse voltage So my peak inverse voltage is twice BP minus VD. Okay. So this is in case of the center tap full wave rectifier. Okay. Now let's discuss another type of full wave rectifier, which is called the bridge rectifier. Full wave bridge rectifier. Okay. So in this case, of course, let's start with this again, half wave rectifier. So I've just copied the diagram. So in this case, I'll have only one secondary windings. Okay, so in case of the center tap, I had two secondary windings of similar turns, and assuming that the magnetic flux of the primary is equally distributed to both. Okay, so now in this case, in case of the bridge rectifier, okay, so instead of that, I'll have a bridge configuration of the diodes. Okay, so here basically what will happen is the number of diodes will increase to double, it will become double, whereas the transformer will become only one, like the half wave rectifier. So this is my bridge rectifier. I have a diode here, I have second diode here. This is my load resistance RL, and here basically we have 4 diodes. So let's name this 4 diode as D1, D2, D3, D4. Okay, so let's connect this source V in here. Okay, let's connect this So what happens is basically when this is positive, right? During the positive half cycle, suppose this is upper half, this is 0 and this is plus BP, right? So what will happen is this diode will start conducting, because it will be D1 will be in forward bias and this will be in reverse bias, and so this diode gets conducting, and finally this is the flow of the current. Okay, so if you see here, this is the flow, right? This red color curve, this is the flow of the current when it is this is high and this is low. Okay, now suppose this is negative in the negative half cycle. Let's consider this negative. So this is at lower potential and this is at higher potential. So now D4 will be in forward bias condition and D2 also will be in forward bias condition, whereas this D3 and D1 will be in the reverse bias condition. So this will be the direction of the flow of the current. So this will be the direction of the flow of the current in the other half cycle. Okay, so this is how my current will flow, and this is basically the direction of the current. Now if you see both the arrows are in this direction. Okay, so that means, right, for both the cycle, for the negative cycle as well as the positive half cycle, I am going to get the direction of the current in the same direction like this. So let's try to draw the time domain waveform. Okay, so this is how my V out is going to look like. Okay, so V out means plus and minus. This is V out. Okay, so and this is how my V out is going to look like. Of course, you can put a ground here. Okay, with respect to ground, if you are, because we are seeing this one. So or yeah, so basically, yeah, this will be a higher potential, this will be a lower potential, because the flow of direction is in this current. Okay, so this is how it's going to work. So this kind of rectification is called full wave bridge rectifier because of this bridge configuration. Now let's try to find out the peak inverse voltage, right? Maybe considering this condition, right? So or maybe considering this condition. Okay, so if you see here, if you see here for this condition, my considering this condition, so let's consider this is at plus BP and this is 0. Okay, so now there will be a diode drop, so this node will be PP minus VD. There's a diode drop here. Okay, and this is of course at 0 potential. So the diode drop experienced by D4 will be the maximum, which is basically this one, BP minus VD, of course 0. Okay, and of course if you see here, this will be the diode drop here, so it will be VD, and this is that BP. So in this case also the D2, it will be BP minus VD. Okay, you can analyze yourself. So the peak inverse voltage in this case is BP minus VD. Therefore my peak inverse voltage in this case is BP minus VD. Okay, here basically the diode drop will be twice. Okay, so it is, in this case it is peak is BP, and at this here it will be BP minus 2 VD, because if you see on the part of the conduction there will be two diode drops coming. So here if it is BP, so here I have BP minus VD, and this is at VD, so the difference is BP minus 2 VD. Okay, so because the two diodes will be coming in the series, so the the peak rectified output will be BP minus 2 VD. Okay, and of course the conduction also will start at 2 VD. Okay, so because both this diode has to be on, so this conduction also will happen at 2 VD. Okay, so yeah, as I was mentioning that the peak inverse voltage in this case is almost half. Let's consider the amplitude voltage maybe 10, right? 10 volt. So and VD is 0.7. So in this case it is 10 minus 0.7, it is 9.3, right? Whereas in this case it will be 2 into 10 minus 0.7, which is approximately 19.3. So this 19.3 is double or approximately double of 9.3, because this 0.7 volt is very small compared to the BP, so it is approximately 2 times. So this is the main advantage of the bridge rectifier, that the peak inverse voltage, the inverse voltage that the diodes are experiencing is half, almost half, but the only disadvantage is that it requires 4 diodes, 2 additional diodes, but diodes are cheap, so it's fine. And the other disadvantage that we can see here is that the drop is 2 VD, means it's approximately 1.4 volt drop. But since our power source is very high, right, it's 220 volt and requirement is not very high, right, it's much smaller, so I can always adjust this N1 and N2 such that I can accommodate this 1.4 volt drop. Okay, so that's why nowadays most of the time this bridge rectifier is preferred, because the reason is that the diodes are cheap. Okay, the problem with this is because we exactly need to locate the the center of this transformer, and the flux should be equally distributed. This there can be a mismatch between the flux distribution, either due to unequal number of windings or because of some structural issues. That's why there will be a difference between this blue and the black waveforms, and because of which you will see that maybe I'll show in the LTSpice simulation that there will be difference in the alternate rectified waveform if there is a mismatch between these two. Okay, these two windings. So because of which this is less preferred. And the other drawback of this one is that this peak inverse voltage is almost twice. Okay, so finally this is the waveform that I have got after the full wave rectification, whether it may be by center tape or maybe by bridge rectifier, but still it is not a perfect DC. Okay, of course the waveform is the waves, or the the signal is above the zero, so the DC component is high, but still it is not perfect DC. We want something which is like flat, right? We have not got it yet. Okay, so we can see there is a lot of valleys here, and we have to fill it, right, to make it perfectly DC. So let's see what's the next step solution that we can take to fill this one to get a perfect DC. So the next step that we are going to take is filtering by the capacitor. So to understand that, let's go back again to the half wave rectifier and see that. So we are going to add a capacitor at the output node, and this capacitor is going to store the charge and make the waveform with a higher DC content, or in one sense it's going to fill the valley that we have mentioned. So let's again go to the half wave rectifier first. So consider a diode, and I have connected a C across this one. Okay, so there is no load resistance, only a capacitor C is connected to it. So let's see what happens in this condition. So when instead of C, when there was a resistance, this was the output waveform. It's a half wave rectifier. Let's connect a ground for reference. Whereas now what will happen is it will not be like this. Instead of this one, the waveform is going to become a little different. Okay, so it's going to be like this. So initially, if I assume that my charge is 0, of course this is at 0 volt, and this will keep increasing, right? This will keep increasing to Vp, and it will keep increasing, and it will be charged to Vp minus Vd. Okay, so then it will increase like this. Okay, and then after that it will start decreasing from this Vp. Okay, so it will start decreasing, then this diode will be off, but the charge will be stored in the capacitor, so it's going to remain constant throughout. Okay, so this is what it is going to happen. Okay, So this is what going to happen. It's going to have a constant DC voltage Vp minus Vd. Okay, we have partially achieved a DC voltage, but actually this is not the ideal situation because we have not connected a load resistance and RL is infinite. But ultimately we want our rectifier or the charger that we are designing to charge some load. So there will be definitely RL. It can never be infinite. So let's see what happens if I connect a resistance in parallel to C. So what will happen is when this is off or when this is going down, right? When this is going down, this is in reverse bias condition. But what will happen is this then this is off, but this capacitor and R and C are in parallel. The capacitor is going to discharge. Okay, so it's going to become something. It's going to go down like this. Okay, it's going to go down like this. But then again, when this becomes higher than this one by a Vd voltage, again it's going to charge something like this. Again it's going to charge till this voltage which is Vp minus Vd, and again it's going to discharge when this goes off. Okay, so this keeps continuing. Okay, so let's draw it properly and let me explain it. So yeah, so now this was the situation when only I should say the R was there. Okay, this is my half-wave rectifier. When only RL was there. Okay, when C was not there, only RL was there. So this was my half-wave rectifier, and we have also seen that when only C is there, it is something like this. So now when R and C is there, what's going to happen is so during the initial phase, it's going to charge till this point, and when the Vin goes down, Vin becomes lower when it goes down, then this diode is in off condition, and because of which the the capacitor will get discharged till the time when this node voltage, okay, till the time this node voltage is higher than this one by Vd. Okay, so basically this is my the red color is the V out. Okay, okay, so in this case, if you see that Vin is still higher than this one, right? Vin is here, so it is Vd higher, right? So it will be Vd it is higher than this V out by Vd. Okay, so yeah, so basically Vin minus V out is Vd. Okay, here, and then it will again charge, and then again it's going to discharge. So this phenomenon is going to continue. Okay, so this is how finally it's going to look like. Okay, so it's going to charge till Vp minus Vd, and then it's going to discharge, and when this Vin again rises, okay, then again it's going to charge, okay, till again this Vp minus Vd, and again discharge. So partially we have achieved this DC, but still there is still some ripple. Okay, still some ripple, and we need to reduce this ripple. Okay, okay, so this this voltage is sometimes called the ripple voltage. So the from here to here, this is the ripple voltage, sometimes represented by VR. So let's try to estimate this VR. What is this VR? Okay, so if you see here from this point to this point, okay, so let's try to estimate, and here this is the time period. Okay, time period T. So and of course for our case the Vin is the frequency is 50 Hertz, right? And therefore the T is 1 by 50. Okay, 1 by 50 Hertz. So yeah, so in this case our T is fixed. Okay, the other thing is, if you observe that although this capacitor is discharging, right, during this phase, but the discharge is very slow, because we have considered that this RL and C time constant, or for simplicity let's just call this R. So this RC time constant is quite high. So here we have assumed that the RC time constant is much larger than T. So we have second as C such that the RC time constant is much larger than C. So that's why this discharge is very small. Okay. So let's try to estimate roughly what is this VR. So if I try to write this discharge equation from this point to this point, right? So I can write my VO, V out, I can write the expression of V out as V out is equal to, here the peak voltage is BP minus VD, and this is discharging exponentially e to the power minus T by tau, okay? And tau, you know, it is simple R and C. So now, suppose we want to know this point at the end of this discharge point. So this point is basically BP minus VD minus VR. So at the end of this discharge cycle is it's going to become BP minus this amplitude minus VR. So it will be BP minus VD minus VR, okay, VR, and is equal to, again, BP minus VD e power time. Of course, this let's call it as delta T. From this point to this point, let's call it to be delta T. So this will be T minus delta T by RC, okay? And assuming that this delta T is much smaller than T, right? We need to do this approximation to simplify this whole expression. So assuming this delta T is much smaller than, you know, I can approximate this whole thing with T. So what I can get is implies BP minus VD minus VR is going to be BP minus VD e power minus T by RC, okay? Of course, it will not be equal, it is approximate. Now again, we are going to do another approximation. We have approximated that this RC is much greater than T. So in this exponential, this is going to become much smaller than 1. So I can approximate this whole exponential with 1 minus T by tau based on the simple mathematics. Since RC is much greater than T, the time constant is much greater than the time period. So e power T by RC can be approximated as 1 minus T by RC. Simple approximation from the mathematics, okay? So if I substitute this one, then what I'll get is implies BP minus PD minus VR is approximately equal to BP minus VD 1 minus T by RC. Okay, so simplify it. Let's write equal to, okay, it's auto approximately equal to, but we can still write BP minus VD, okay, and then this is going to become T BP minus VD by RC, or in one sense this and this gets cancelled. Okay, so finally what I'll get is T and BP minus VD by RC. Let's call this BP minus VD to be VM. So let BP minus VD is equal to VM. So what it means is the maximum voltage which is occurring, okay, the amplitude of this half wave rectified output is VM. So this is VM. So therefore my VR is equal to T Vm by Rc, or is equal to 1 by, okay, so this is the final expression. This is the final expression of the ripple voltage. Okay, so the ripple voltage is directly proportional to Vm, or basically the amplitude, or the amplitude of the sine wave that I am applying, or the input signal. It is the inversely proportional to R and C. Okay, and of course F. So in our case, the F is almost constant. It's almost constant. So the thing that we have here is the R and C. R is also mostly defined by the customer because the load is approximately fixed. And of course, the only thing that we have is the C. So what it means is that higher the value of C, lower will be my ripple voltage. Okay, so higher the value of C, lower is my ripple voltage. So one may say that okay, I can increase the C very high and I can get almost flat because it is not going to discharge, right? It's going to store discharge. So but this is also not possible. Why? Because so there is a limitation. Because if you see here, during this phase delta t, the capacitor is getting charged. So the current is going to flow and charge the capacitor. Okay, so what will happen is during this period there will be a peak amount of current that will be flowing through this diode and to charge this capacitor. And higher the value of the capacitor, higher will be this current. Because, or in case of this capacitor, we know that the C is equal to IC is equal to C dV by dt, right? So higher the value of capacitor, higher will be the current required to charge this capacitor in this short delta t time. Okay, and if it exceeds some value of this diode current, this diode may get spoiled, because generally if you see the data sheet of this diode, Imax value will be given. So the current flowing through this diode should not cross, right? It may be 200 or 300 milliampere, so it cannot cross beyond that, and because the diode is going to get spoiled. So this limits the value of C, or this defines the upper limit of this capacitor C. There is no lower limit, of course. We want as high as possible, but we have to make sure that this C should not be so high that the current required to charge this capacitor becomes too large and it spoils this diode. So the conclusion is C, okay, C cannot be very large, because if it is too high, current required to charge it may exceed the maximum current allowed through the diode. Okay. Okay, so the conclusion here is, yes, we have partially achieved the DC, but it is not yet perfect. Okay, so we have to go to one more stage solution to get the perfect solution. So okay, this was the ripple voltage for a half wave rectifier. For a full wave rectifier, it will be just by 2, okay, because the frequency is going to become double, right? So if you see here, for a full wave, the next waveform is going to come here, right? So the T is going to become 2 by 2, so the frequency will become 2 times of the F, okay? So for full wave rectifier, so the time period is going to become half T by 2, or the frequency is going to become 2 times, okay? So this will be finally my ripple voltage will become half in case of the full wave rectifier compared to the half wave rectifier. So now let's see all these things whatever we have discussed in LTSpice. So yeah, this is my LTSpice. First we are going to design the half wave rectifier, then we'll design the full wave rectifiers. So you can go here and you can get this inductor first, okay, and then you can just Ctrl R, rotate it, okay, put it here, get one more inductor. So there are two kinds of inductor. You can flip it, Control E and then Control R. So there are two types of inductor. One inductor without having this dot, right? Other inductor with having this dot. Dot means it gives the direction of the flux. Okay, so this is important. So to do the half wave rectifier, just go here and get the voltage source. So this is my AC mains current, okay, and you can just connect here. Sorry, this is my AC mains voltage, okay, and connect here. Now get a diode. To get a diode, you can go here, or if you go to component, you can just type diode. Click here, rotate it, Control R. Then do the connection. And then put a ground here. And maybe let's label this as V out. Sorry, I need to connect a resistor here. You get a resistor from here. You can connect it. Okay, so now I need to select a proper diode for this. So right click and pick a diode. We are going to use this diode 1N4148. This is from On Semiconductor. Okay. Click OK. Okay. Now this is done. Select the resistor and make it maybe 1 kilo ohms, 1K. Okay. And I need to define the AC mains. So go to Advanced. Sine, okay, so the amplitude wise it will be 311 because 220 volt is the RMS and the amplitude corresponding to 220 volt is 311 and the frequency of course is 50 Hertz. Okay, this is done. So now for the inductor, let's make it maybe 1 millihenry and this one maybe around 300 microhenry, 300 U. Okay, and let's go for a transient simulation. So for that, in the SPICE directive, you can right click, help me edit, analysis command, transient analysis. So maybe it is 0.1 seconds. So here we are supposed to do the time domain simulation, which is called the transient analysis, because I want to see the waveform will change in the time. So I think I need to move this one because you can drag it the component value. Okay, we are doing a We are doing a transient analysis because we want to see the variation of the waveform with respect to time. Okay, and now finally, one last thing is remaining. We need to couple these two inductors. So to do that, go to SPICE directive here, type K. This is L1 and L2. So type L1, L2 will have a coupling constant of 1. Okay, so although 1 is the ideal coupling constant, but in real life it is always lesser than 1. But just for trying to see the working principle here, we have made it 1. Okay, save it and run the simulation. Okay, so here we need to have some series resistance with this inductor, otherwise it will show some warnings because both of them are ideal and there is no resistance in this part. So make it just add a series resistance of maybe 2 ohms. Here also you can add a series resistance of maybe 2 ohms. Run the simulation. Okay. So just plot it here. So you can see that this is a half-wave rectifier and this is the input signal to this. Okay. So this is my input, but after half-wave rectification, it is something like this. Okay. So of course, because my amplitude here is quite high, it has gone to almost around 26 volt. So that's why the VD drop is very negligible. I should say that it's very small. But if we make this smaller, maybe just make it 40 micro, okay. So we can see here that VD drop is significant here, okay. Yeah, so this is my half wave rectifier. So let's change it to full wave center depth rectifier. I'm putting one more diode here, and of course I need to put one more inductor. Again, note that the direction of the flux is important here, and it should be same. This board should be connected here together, and I should connect a load resistance here. Load resistance here. Connect it to the center tap, and maybe connect a ground. If the ground is not connected, it's not going to simulate because the SPICE requires a reference count for doing the simulation. So resistance, make it 1K again, the load, and let this diode be the same diode as the previous one. Save it. Now we have three inductors, L1, L2, L3. So I need to right click and edit it and make an L3 as well, because then only it's going to simulate, because I need to couple all the three together, okay. And of course this value will be 40. Run the simulation again. You can see that the V out is now full wave rectified, okay. So you can see here this is my input, okay, and let's name this node. So maybe in this case let's name this node as VA, and let's name this node as VV. Okay, this is my V out, and of course I can plot now the VA. And this is VV, okay. So you can see here that VA and VV, and the V out is fully rectified. The black one is the V out, okay. And of course you can play around it. Of course you can play around with it. If I change this value, instead of 40, if I make it 50 maybe, okay. So, and then run the simulation again. So you can see here that this red VA and VV are different, and because of which, if you see the V out, only the V out, the alternate, the waveforms have different peaks. So let me delete these two waveforms, and then you can see clearly. So you can see, if I zoom this V out, because of this unequal, because of this asymmetry, you can see that the alternate peaks have different values. So this also you may observe when you do the experiment in the lab, okay. Okay, now let's change this to bridge rectifier. Okay, let's design the full wave bridge rectifier. So to get the full wave bridge rectifier, just put the 4 diodes first in the bridge configuration. Let's connect them with the wires first. Put a resistor. Rotate it, Control R. And maybe you can just delete this one. And name this 4 resistor. Okay, select the same diode for the 4 diodes. So we have selected the same diode as we had done as the one in the center tab. You can maybe move this level so that there is no. You can just save it, and the resistor can be 1 key, and label the output as V out. Of course, you need to put a ground on the other side, otherwise it will not work. Let's call this as VA. And this as VV, so that we can plot the input that is provided. So here we need to plot this difference because this is coming from this transformer, so the differential voltage is important. Okay, now run the simulation and you can plot this V out. Okay, so you can see that this is a full wave rectified output, and you can plot the difference. The input is the difference between this one and this one, so you can go click here and then click here. You can see that this is the input, right? The blue color is the input, and the black color one is the output. We can find out the drop, right? The diode drop that has occurred. Definitely, we can just click here, okay, and go here. This is cursor number 1. Again, you can click one more and get the cursor number 2 here, right? And you can see the difference. So if you see here, the difference is 1.38. So that means it's close to 1.4, okay? Or 2 diode drops. Okay, so this is the bridge rectifier, okay? Okay, this is my full wave rectifier. So if I just simulate it again and try to plot the V out, so this is what I'm going to get. Okay, this is my rectified full wave rectifier. Okay, so now if I try to put a capacitor, let's see what happens. So if I put a capacitor here, let's put some value, maybe 10 microfarad, okay, and just run the simulation again. So you can see here, right? You can see here, this is the output, okay? So if you see here, the input is something like this. So after using this, capacitor, we can get the, the filtered output, okay? And of course, here what we have considered is the load is quite, quite small. So if I increase this load, maybe let's make it, instead of 10K, if I make it 5K, okay, I'm reducing it by half, okay. Okay, so this is my waveform, and just let's bring the cursor and see what is the value of the ripple voltage. So this is my cursor number 1. Just click it here once more and you get cursor number 2. Okay, and the difference between cursor 1 and cursor 2, you can say that it's around 247 or 250 millivolts. So that's my ripple voltage, around approximately 250. Okay, so now if I make this resistance half, I'm supposed to make my ripple voltage double because it is inversely proportional, right? It is quite obvious, right? If I decrease this resistance, my discharging time will decrease, right? So now if you see here, the ripple voltage has almost doubled, okay? So approximately double, of course, because we have approximated it, so it may not be directly double, but you can see here, right? It's now from 250, it has gone to 460, so close to 500. And if I make this capacitor maybe 20, right? I can now get back my same ripple as the previous one, okay? So again, it is close to again 250, okay? So so by adjusting the value of this capacitor and this resistor, we can make the ripple small. But imagine I have very small resistance, maybe just 1 kilo. So you can see now the ripple will be huge, right? And to compensate that, I have to increase it. Maybe let's make it 100, okay? Okay, so then again it is small, but as we know that as we increase this as we increase this capacitor, the current is going to increase. The current, if I just plot this current, okay, so we can see this current waveform, and this is the axis for the current, okay. So if I just use my cursor here, right, so click here and get the cursor here. So you can see that the current is approximately, you can see the ID in the vertical is 26 milliampere, okay, and yeah, this is 26 milliampere, and if I increase this one, if I increase this capacitor, right, my current is going to increase, okay, my current is going to increase. So for example, suppose I have made this my load to 500 ohms, and because of which I have to make this to 200 ohms, okay. So if I just run it, so you can see here it has increased from 26 to 44 milliampere, the peak value, okay. It's the charging time of the capacitor. And of course, initially you can see here there's a huge amount of current that is flowing through the capacitor. The reason is because initially there was no charge in the capacitor, so we have to charge it, right? Initially you can see here the V out is almost 0. So because the initial charge of this capacitor was 0, so a huge amount of current will flow through this diode, okay. But in other case also, the current is going to increase, okay, with increase in the I should say that with increase in the capacitor. And of course, if this peak value also increases, the capacitor current is also going to increase. For example, if I make this one double, so currently it is 44 or 47, and if I increase this one, so you can see here that my ripple has increased, and then you can see that the current also has increased to 74 milliampere, okay. Okay, with this we will end the discussion on the rectifier. Thank you.